Hello everyone, I'm Arun Prohit. Welcome you all in this short lecture on basics of air conditioning. After watching and learning through this video, you should be able to differentiate the dry air and atmospheric air. You must be able to define the concept of specific and relative humidity of atmospheric air. You must also be able to define dew point temperature and wet bulb temperature. Now, let us begin with the understanding of air and its component. Air is a very interesting working substance because it includes gases like nitrogen, oxygen, and small amount of other gases. Usually, this gas mixture is termed as dry air. Why do we call it dry air? Because this mixture of gases do not include the moisture which is also be there in the atmospheric air. Another point that the proportion of these components of air do not change. Do not change means it since the gases are very far from their vapor condition or they are not liquefied easily. That's why we call this part of air as dry air, since it also includes water vapor. But the proportion of water vapor in air is variable. It is because of the condensation and evaporation process that could happen over the free surfaces of oceans, lakes, rivers, etc. And even from the human body, the perspiration may change the moisture in the room air. Therefore, atmospheric air pressure can be given as P is equal to the partial pressure of dry air plus the partial pressure of water vapor. Or we can write it as P is equal to PA plus PV, where PA is the dry air partial pressure and PV is partial pressure of water vapor at the same temperature. In the study of air conditioning, we use many basic terms. Here we are taking up one of the important basic term called specific humidity. To understand the concept of specific humidity, let us assume a space or a closed room where we have room air, which includes the dry air as well as water vapor. So the mass of air inside the room would be given as Ma plus Mv. Now, the specific humidity, which is also termed as absolute or specific humidity or even humidity ratio, usually denoted by omega, is defined as the mass of water vapor present in a unit mass of dry air. That means in the room where we have total mass of air to be small m, including the mass of air Ma plus mass of vapor Mv, so the specific humidity omega would be given as Mv divided by Ma, that is the mass of water vapor per unit mass of dry air. Ma, remember, Ma represents mass of dry air, the part of the air that cannot be liquefied, whereas Mv denotes the mass of water vapor that can easily change. Even the specific humidity can be given in terms of partial pressures. It is given as 0.622 partial pressure of water vapor divided by partial pressure of dry air. The unit of specific humidity would be, in this case, given as kg of water vapor per kg of dry air. Now let us take another important concept which we use in air conditioning, The concept is of saturated air. Friends, we know that the mass of water vapor mv is a variable quantity in the atmospheric air. It is zero when we have dry air, and it increases as we add water vapor in this dry air. And this addition of water vapor could be done by vaporizing water body in the air. So, corresponding to the air pressure and temperature, a condition of air arrives when further addition of water vapor is not possible. That means the water vapor which we were adding into the air would come to a condition where further addition of water vapor is not possible. That means air cannot hold further moisture, and this condition is called saturation, and the air in this state is called saturated air. Saturated air is saturated with water vapor. Further addition of water vapor would condensate it. That means further addition is not possible. If even then we add some water vapor, it would get condensed automatically. Another important term which is widely used in air conditioning as well as in our day-to-day life is relative humidity. It is defined as the amount of moisture that the air holds relative to the maximum amount of moisture that the air can hold at the same temperature. That means we know in actual the moisture available in the air might be, say for example, mv, but we know further addition of moisture is also possible. But when it becomes saturated, at that point the moisture in the air at the same temperature would be mz. So this mz quantity of moisture is greater than the mv quantity of moisture. So the ratio of the mv quantity of water vapor to this mz quantity of water vapor is called as relative humidity. So the humidity means the amount of water vapor, relative means relative quantity of water vapor at saturation condition and in actual condition. So relative humidity phi is defined as mv divided by mz, and even it is expressed in terms of the partial pressure of water vapor, that is PV divided by PZ. PV is the partial pressure of water vapor in the air, and PZ is the water vapor partial pressure when the air becomes saturated. The relative humidity is strongly affected by the temperature value. The air at higher temperature can hold larger quantity of moisture as compared to the air which is at lower temperature. Even more important for air conditioning is that the human comfort is strongly affected by air temperature as well as relative humidity. Now let us take an example that there is a room where air is at 1 atmosphere and at 25 degree centigrade. This air would constitute two masses, one Ma, that is the mass of dry air, plus the mass of water vapor, that is Mb. Now if Ma is 1 kilogram and moisture mass Mv is equal to 0.01 kilogram, and suppose the maximum amount of water vapor that this air can hold is 0.02 kg, then specific humidity or humidity ratio would be given as the mass of water vapor in actual available there in the room, that is 0.01 divided by 1. So it is 0.01 kg of water vapor per kg of dry air, whereas the relative humidity would be the mass of water vapor that is there in the room upon the mass of water vapor when it becomes saturated with water vapor. So it is 0.01 divided by 0.02. So relative humidity becomes 50%. Remember, relative humidity is unitless, whereas specific humidity is given as kilogram of water vapor per kilogram of dry air. In air conditioning, we also use dry bulb and dew point temperatures many a times. What dry bulb temperature is? Ordinarily, whatever temperature we measure with the help of a simple thermometer, that temperature is termed as dry bulb temperature. Whereas the dew point temperature, it is defined as the temperature at which condensation begins when the air is cooled at constant pressure. Suppose when we have a summer's day, in the morning we find that very small water droplets are there on the leaves of the trees. Why it happens? Because in summers during the daytime, water body becomes vaporized and adds water vapor into the atmospheric air. But during the night time, when the temperature decreases, and while decreasing the temperature, the water vapor that the air can hold will start decreasing, and ultimately when air becomes saturated, at that point the excess amount of water vapor is condensed on the colder surfaces like the surface of a leaf on a tree. So these fine droplets are called as dews. That's why the name suggested is dew point temperature. In other words, we can also say that dew point temperature is the saturation temperature of water corresponding to its vapor pressure. Now, to understand the concept of wet bulb temperature, let us first learn the concept of adiabatic saturation temperature. Consider an insulated channel as shown in figure. What we see that on the one side of this channel, unsaturated air at low temperature T1 is available and it flows at this T1 temperature over this liquid water. The temperature of water is comparatively lesser. So what will happen? Since the air is unsaturated, that means air still has the capacity to hold moisture, and since there is the difference of concentration of water vapor quantity in liquid water and unsaturated air, and because of that some part of liquid water get evaporated and that consumes the part of heat of air for vaporization. So since air is supplying the heat of vaporization, so air cools down, and since the moisture from this liquid water body gets added into this flowing stream of air, and that's why this air becomes moisture rich. And finally, when it comes out at two section, what we get, the air, since the channel is quite long, so the air comes out from this channel would become saturated. That means whatever quantity of moisture it can hold, it has already acquired it. So it has become saturated, and while it is becoming saturated, since it has sacrificed some of its heat, so its temperature get decreased. So the temperature T2 is lesser than the temperature T1, and since it is saturated air, so its relative humidity has become 100%. Now finally, when it comes out at T2 temperature, this T2 temperature is what we call as adiabatic saturation temperature. Why we call it adiabatic? Since the channel was insulated, so there was no heat interaction with the surroundings. The heat required for vaporization of liquid water was gained from the air internally. So ultimately Holistically, the process was adiabatic, and this heat exchange happened inside the air stream or inside the working fluid. Now let us learn the concept of wet bulb temperature. In case of adiabatic saturation temperature, we used an insulated long channel where we contained some water, liquid water inside it. The same process can be done using a thermometer, an ordinary thermometer, whose bulb is covered with a cotton wick, and this cotton wick is saturated with water, and the air for which we want to measure the wet bulb temperature is blown over this wick as shown in this figure. Ordinary thermometer covered with wick, liquid water is there, and this wick is saturated. Since air is blown over it, what will happen? The same thing will happen as we have already seen in case of adiabatic saturation process, and this thermometer will measure the temperature, which will be called as wet bulb temperature. Obviously, this wet bulb temperature will always be lesser or equal to the ordinary dry bulb temperature. If the air is saturated, the blown air is saturated, then dry bulb and wet bulb temperatures would be same. And if air is unsaturated, then wet bulb temperature will be lesser as compared to dry bulb temperature. So here we are concluding today's short lecture. Hopefully you enjoyed it and learned the basic concepts related with air conditioning. Thanks. Have a good day.